Hi everybody, so we're going to focus on redox reactions today. A redox reaction is where both reduction and oxidation are happening to species within the reaction. So if we start off first by reminding ourselves what we mean by reduction and oxidation. Now, I always find it easiest to remember oil rig. So the idea that oxidation is loss of electrons and reduction is gain of electrons. Now, that should ring some bells from GCSE. Now, overall then, this means that any redox reaction will always involve the movement of electrons. And we are expected to be able to determine in a given reaction what is being reduced and what is being oxidized. Now, for reactions that undergo redox, we can write them as half equations. So as part of this session, what we're going to do is we're going to build up to writing half equations and then combining these to write full redox equations. So if we start off just by looking at oxidation states. Now, any element can be given an oxidation state. If it's an ionic compound, it tells you how many electrons have been lost or gained compared with the element in its uncombined state. In a molecule, it's the distribution of electrons between elements of different electronegativity. Now, there are some given rules to working out oxidation states. For example, we've got the idea that uncombined elements always have the oxidation state of 0. Now, some elements are always the same regardless of the compound. You are expected to learn these, and I have emailed out the sheet to go with it. So make sure that you remember the key rules. Now, we're just going to go through a couple of examples. So, if we start with NH3. Now, I would always recommend working your way through each of the elements, identifying which ones you should know because of the rules first. So, if I look at my rules, I know that hydrogen is always +1 except in metal hydrides. So, I'm just going to label the hydrogen as +1. Now, I've got 3 hydrogens in this compound, meaning that the overall oxidation state or the overall positive charge from those hydrogens is +3. Now, the rules state that in a compound, the sum of all oxidation states must be 0 so long as it's neutral overall. Well, we've got a neutral compound, so that means we're trying to make it so that it's 0 overall. So if on this side it works out as +3, it means that N must be -3. So my oxidation state for N would be -3 and H would be +1. If I take another example, this time HNO3. Now this time I've got 3 different elements, so I need to work through and identify which ones I should know already. So same rules as before, hydrogen is always +1 except in sodium hydride. So let's make that +1. And oxygen is always -2 except in peroxides. So we've got a compound that is neutral overall, so our aim is to make it 0. We've got 3 lots of oxygen at -2, so we would have overall -6 here. Hydrogen, we said, is +1, so in order to make that neutral overall, the N must be +5. Notice how N has 2 different oxidation states in this situation. Now, if we take a different example that is actually charged, so I'm going to take SO, in fact, let's do it up here, SO4 2-. This time, my molecule isn't neutral overall. It has a charge of -2. So overall, my oxidation states, rather than equaling 0, must equal -2. So we know that oxygen must be -2 as it is not a peroxide. There are 4 of them, making it -8 for oxygen overall. Now we're trying to get it to -2. So this means that sulfur must be +6. Okay, So we've got 3 different types of compounds there. Let's have a look at one more example. So we'll go for Cu2O. Again, the idea that oxygen must be -2. This isn't a charged compound, so therefore it needs to be neutral overall. So we have 2 coppers that together must equal +2. So each individual copper will have an oxidation state of +1. So now that we can identify the oxidation states, what we can start to think about is putting these into half equations. Now I'm going to start quite simply with just the conversion of atoms into ions. So if I want to write an a half equation for the conversion of copper 2+ into copper, the first thing we need to do is identify whether or not it's being oxidized or reduced. So we've gone from a +2 oxidation state to a 0 oxidation state, meaning that the copper has had to gain electrons. Specifically, it's had to gain 2 electrons. This means then that I'm going to put my 2 electrons on the left-hand side with my reactants. If I was to take another example, this time looking at chlorine, so we're going to take a chloride ion and convert it into a chlorine molecule, remembering that chlorine is diatomic, so we will need 2 chloride ions. This time we've gone from a negative oxidation state, -1, to 0. So what's happened here is that the chlorine has been oxidized. It's lost electrons. So we put the electrons on the right-hand side as one of the products from this equation. And to make it balance, we're going to need 2 of these. Now, again, this should look familiar from GCSE. Things get a little bit more complicated at A level. So, if we look at some different examples, this time we're going to use a compound. So we're going to take VO with a 2+ charge, and we're going to convert it to VO2+. Now, what we're going to try and do here is put together a half equation for this reaction. Now, the very first thing that you should do here is calculate the oxidation states on either side of the equation. This will allow us to identify which side our electrons go. So, if I have a look here then, I've got an oxygen, which must be -2. I've got an ion, so it's not going to be neutral overall. It's actually going to be 2+ overall. So to make that, my vanadium must be +4. On the other side then, I've got oxygen that's a -2, but this time I've got 2 of them. So I'm going to have a -4 charge, and I'm trying to get it to +1 overall. So I'm going to need to have vanadium at +5. So I can see here then that to get from +4 to +5, I have to lose electrons. So the next thing I'm going to need to do is have a look at where my electrons will go. Well, if I was to rewrite this, I've now got VO2+ to VO2+, and my electron is going to go on the right-hand side because it's been lost. Now, this is all well and good, but I haven't yet balanced the oxygens. So the next thing I need to think about is how I'm going to do that. Now, if I have oxygens in my compounds, I'm going to balance these with waters. So I can see that I've got 1 atom of oxygen on the left and 2 atoms of oxygen on the right. So the way to balance that is I'm going to add some water on the left. So I can see that my vanadium's balance, I've got 1 on this side, 1 on this side. I can see that my oxygen's balance, I've got 1, 2 on the left hand side and 2 on the right hand side. However, I now have another issue. Because I've added water, I've now added some hydrogens into the mix. So what I need to do is account for those hydrogens. Now, the way I'm going to do that is I'm going to use H pluses. So, on the left-hand side, I've got 2 hydrogens that are unbalanced. I'm going to balance those by putting 2 H pluses on the right-hand side. Now, I should be able to look at my equation and see whether it balances. And I'm going to start by thinking about it in terms of atoms. I do apologise, can't see that. So, just checking the atoms then. I've got 2 hydrogens here, 2 hydrogens here. 1, 2 oxygens, 2 oxygens here. So they balance. I've then got 1 vanadium on the left and 1 vanadium on the right. So my atoms balance. But the next thing I have to make sure it does is that my charge is balanced too. So if I look on the left hand side, I have an overall charge of 2 plus. If I take a look at the right hand side, I've got a plus, a minus and 2 pluses. This plus and minus will cancel each other. So again, on the right hand side, I have a charge of 2 plus. So my equation does fully balance. And my final answer, if they ask me this in an exam question, would be that the half equation for vanadium would be H2O plus VO2 plus produces VO2 with a plus charge, an electron and 2 H pluses. Okay, so if we take another example then. So we'll use the example of BrO3 minus to Br2. So we're going to follow the same steps. The first thing we're going to do is identify the oxidation states of all of the atoms. So oxygen must be -2. We've got 3 of those, so it'd be -6 overall. And then our iron has an overall minus charge. So Br would be +7. Sorry, +5. Because we've got 3 lots of -2 would be -6, and we're trying to get to minus, so it'd be +5. Br then, because it is in its elemental form, will have an oxidation state of 0. So we've gone from +5 to 0. We have gained 5 electrons, or Br has been reduced. So now that we know this, we can rewrite it with our electrons. So BrO3 minus plus 5 electrons will give us Br2. Now this example is a little bit different to the last one because I can see that my Brs do not balance. So there's an extra step here. I'm going to have to balance the equation for Br. Because I've got 2 Brs on the right hand side, I'm going to need 2 lots of BrO3 minus, meaning that I'm actually going to need 10 electrons in this case. So let's rewrite that then. plus 10 electrons will make Br2. Now, because we've got oxygen in this reaction, we're going to need to balance that with some waters. We've actually got 6 atoms of oxygen on the left-hand side, so we're going to need 6 water molecules. Our next step then is to balance the water molecules with H pluses. So we've got 6 lots of H2, we're going to need 12 lots of H plus on the left-hand side. So we can double check our equation here. First of all, checking it balances for atoms. We've got 12 hydrogens on the left, 12 hydrogens on the right, 2 Brs on the left, 2 Brs on the right, 6 oxygens on the left, 6 oxygens on the right hand side, and we can now check it for charges. On the left hand side, we've got 12 H pluses and overall 12 minuses. They will cancel out, meaning that the left hand side is neutral, it has no charge. Looking at the right hand side then, we can see that is also neutral and our equations balance. So, moving on from that then, we have to be able to take half equations and combine them together. So, let's take some examples. Let's start off quite simply. If I was to take the half equation for the oxidation of iron into iron 3+, and I'm going to combine that with the reduction of chlorine to make chloride ions. So, if I was to take these half equations and combine them together, the first thing I need to do is ensure that both half equations have the same number of electrons. So I can see here we've got 3 electrons and 2 electrons. So I'm going to need to make it so that there are 6 electrons on either equation. So I'm going to multiply the iron half equation by 2 and the chlorine half equation by 3. So if I rewrite those then, I've got 2 Fe's to make 2 Fe3 pluses and 6 electrons, and I've got 3 Cl2s and 6 electrons to make 6 Cl minuses. Now that the number of electrons on either side is the same, I can combine those two equations together. So, all of my reactants will be 2 Fe's plus 3 Cl2s and 6 electrons, which produces all of my products. So now I've got 2 Fe3 plus and 6 electrons and 6 Cl minuses. If I just move that up so you can see. I do apologise, it's a little bit big, but I can see straight away there then that on either side I've got 6 electrons. Now those electrons we can cancel, leaving us with 2 Fe's plus 3 Cl2s, which makes 2 Fe3 plus and 6 Cl minus. So our full redox equation then is that, or we can combine those two ions together in our products, which will give us 2 FeCl3. So if we take up one that's a little bit harder then, let's have a look at combining one of our ones from before. So if we take the example of magnesium burning in oxygen. Okay, so we're going to work through all of the steps here. I've got the reaction 2 magnesium plus O2 makes 2 magnesium oxides. So, the first thing we're going to do is write out some half equations. So, what we're going to do is we're going to look at the oxidation states of each of the compounds or atoms or molecules. So we've got magnesium on its own is going to be 0. Oxygen on its own is going to be 0. When combined with magnesium, oxygen is going to be -2, so magnesium will be +2. So if I was to write my half equations here, what I'm going to have is magnesium becoming magnesium 2+, and it is losing 2 electrons. Oxygen is O2 becoming O2-, and it is gaining electrons. And actually, to make this balance, we're going to need 2 lots of O2 ions, and so 2 electrons. To combine this then, I can see already that I have the same number of electrons either side of my equation, meaning that I can just take magnesium and O2 and it will make Mg2+ and 2 O2-, or 2 lots of MgO, which is what we started with in the first place. Now we might be asked to take this even further. We could be asked to combine equations that contain oxygens and hydrogens. Now this will just work in exactly the same way. So if I find another example, if you just bear with me, combining half equations, there we go. So let's take a look at these. If I start with the half equation, MnO4- plus 8H pluses and 5 electrons will make Mn2+ and 4H2O. So I've already worked out the half equation there. I'm going to combine that with the half equation for chlorine. Now, immediately I can see that I've got different numbers of electrons in both half equations. I have missed off my minus on my 2 electrons, my apologies. What I'm going to need to do here is start by making it so that there is the same number of electrons for either half equation. So I'm going to times the top equation by 2 and the bottom one by 5. This will make it 2 MnO4- 16H+, 10 electrons, 2 Mn2+, and 8 waters. The bottom one will become 10 Cl-, produces 5 Cl2 and 10 electrons. So now I've got the same number of electrons on either side of my equation. I can combine all of that together. Now, there's a lot more going on here. Notice when I write these out, I try to keep the arrows beneath each other so that I can follow what is on either side. So all of this is my reactants. Now I'm going to try to write this a little smaller so I can fit it all in. We've got 2 MnO4- and 16 H+, and 10 electrons, and 10 Cl-, which will make 2 Mn2+, and 8 waters, and 5, I'm not doing a good job of fitting it all in, 5 Cl2s, and 10 electrons. So now that I've made my electrons the same, what I can do is cancel them. So my final equation here, now that I've cancelled my electrons, is 2MnO4 minus plus 16H pluses and 10Cl minuses to make 2Mn2 plus and 8 waters and 5 Cl2 molecules. Long answer. Now sometimes we can get H pluses on either side of the equation. If it is that you end up with H plus on this side and on this side, cancel as many as you can. So if there's 10 on the left and 2 on the right, it will cancel down to 8 H pluses on the left hand side. It is worth practicing these. Use all of what we've got from today's session together. Start at the beginning, write out your half equations using the oxidation state rules. When you've got two lots of half equation, practice combining them together.